Thank you, Andrew. Well, thank you very much for the invitation. I think my task is to sink you to the depths of despair, and then Stuart is going to lift you up tomorrow with, what we do about it. So I'm a paleontologist and sedimentologist, and I'm going to give you an example of a bit of work that actually we did a while ago with a PhD student of mine. And the results were surprising. We didn't expect them. So mass extinctions, climate change, and ocean acidification. So we tend to think of the evolution of life as this sort of very linear narrative of starting with the origin of life, very, very simple, and an ever-increasing march towards complexity, and hominids are often put at the very end here. Now, of course, this is not the truth at all. Life has been interrupted by some very, very dramatic events, mass extinctions. And these really do reset the evolutionary clock. They reset the whole direction of evolution. So they are catastrophic, but nonetheless, they're very, very significant. There have been 5 in the last 550 million years or so, and of these, by far the biggest, which is the one at the end of the Permian, 252 million years ago. It was almost certainly caused by a massive outpouring of volcanic lavas on what is now present-day Siberian platform. They're known as the Siberian traps. And they cover today a huge area, about the volume of lava that was extruded over several millions of years was something like 500,000 cubic kilometers, a huge amount. They're accessed through all the rivers of Siberia, but they're still relatively difficult to get to, and the dating of this exact event, the exact dating is still underway. But one of the things that terrestrial volcanoes produce is a huge amount of various types of gases. And in particular, if these eruptions are prolonged, they produce a huge amount of carbon dioxide, which we all know is a very strong greenhouse gas. Now, this these Siberian traps, they were probably generated by a hotspot because they were in the middle of a cratonic area, or at least a continental area, and they punched through a series of strata, including carbonates. So in fact, what was produced was not only magmatic CO2, but also CO2 as a result of hydrothermal reactions with carbonates. So it produced a huge volume of CO2. In the sea before, we had very happy, biodiverse ecosystems. This is a sort of reconstruction of a reef at that time. But afterwards, extremely depleted ecosystems, often just algal scums like this on the surface in the seas, seafloor, or very, very low diversity communities. It's just a single species of bivalve covering the shallow marine areas. On land, again, a reconstruction. These are very primitive but huge predatory reptiles that dominated the terrestrial ecosystems, and a lot of sort of various types of primitive ferns. Afterwards, that whole part has gone, that whole part of the ecosystem, terrestrial ecosystem, was hugely diminished. So this event in the history of life, so this is the last 550 million years or so, is a really dramatic pulse of a loss of biodiversity. You can see this is where it sits amongst the other 5 mass extinctions. And in terms of evolution, this got rid of all the old Paleozoic ecosystems. So in effect, this is a very common idea or fundamental idea in ecology, which is that once an ecosystem has evolved, it will sit there forever. By forever, I mean millions of years, and still until some catastrophe wipes out the entire ecosystem. This is this theory called incumbency. And in effect, what this extinction did, it removed about 95% of all species and removed these incumbents. And it allowed the modern world to be ushered in. So it allowed the rise of all sorts of groups, some of which are still with us today. Others, like the dinosaurs, of course, appeared after this. But it was a real sort of step change in the modernization of our planet. As a sort of thought experiment, really what would happen if you had this huge amount of eruptive material from the Siberian traps? The major issue is that it produces this greenhouse gas, CO2, and that will lead to global warming. But on land, it would produce, it would have noxious emissions, and these would particularly attack terrestrial ecosystems, and in effect produce acid rain, and you can see this chain of events. but effectively leading to this terrestrial mass extinction. Now, if you heat up the planet very, very rapidly, one thing that happens is that methane hydrates and gas hydrates become unstable. And we know this is happening today. So these are a series of images from a methane hydrate mound in the Arctic Ocean, and they are starting to become gaseous. And methane is a very, very virulent greenhouse gas, more than 20 times more virulent than CO2. So in effect, you end up with what's called a runaway greenhouse. So although the primary causes were the volcanic eruption, they lead to a whole knock-on set of events, including a really sort of a positive feedback here with even more global warming as a result of this methane, these are methane destabilizations. This is just a methane vent being lit in the Siberian tundra. So we have a potential runaway greenhouse at this time. So one of the things that happens with these catastrophic events, and they've happened many, many times in Earth's history, is they show up in the carbon cycle in the way that we try and measure the changes in the carbon cycle. So the carbon cycle operates over many, many timescales. The short one is just a very short-term photosynthesis and respiration cycle between CO2, life in terrestrial life and life in the oceans. And of course, there's a constant exchange and equilibrium between CO2 in the atmosphere and CO2 dissolved in the sea. But on a longer time scale, what happens is that as CO2 rises, you get increased warming climate. That causes increased weathering of rocks, and they produce a change in the dissolved solutes of the oceans. And those dissolved solutes are calcium and carbonate, and those go together to form the shells of marine life, which forms limestones. And this is by far the biggest store of carbon on the planet. It dwarfs all other carbon on the planet. And naturally, that store will sit there for millennia, well, for millions and millions of years, hundreds of millions of years, until it finally gets subducted, and then comes out. The carbon is lost through volcanic gas emission. And organic matter, of course, has the same fate. That will sit there geologically over a very, very long time. But of course, what's happening now is we're short-circuiting all this carbon, which is now preserved as fossil fuels. We're short-circuiting the carbon cycle and then placing that carbon much more rapidly into the atmosphere. One way we sort of get at trying to understand the dynamics of the carbon cycle on a geological timescale is, luckily, all these different sources of carbon, atmospheric, organic matter, methane, and limestones have a different ratio of carbon isotopes. And the two stable isotopes we tend to use are carbon-12 and 13. And this gives us a ratio, delta C13. And because these are fingerprinted, it means that when we look at the geological record through time of these carbon isotopes, we can make a judgment as to what the source of carbon has been and how this cycle has in effect been upset. So if we look at this record through geological time, so this is about 2.5 billion years, you can see there are phases when very little happens, but other times when there are these huge oscillations in this signature. And here is the end-Permian extinction. And it's a dramatic shift, this big negative pulse in carbon, which is commensurate with this huge outpouring of magmatic CO2, which has this very, very negative signature. These events, by the way, are the snowball Earths of when the Earth became semi-frozen over. And there's a very dynamic carbon cycle, for example, in relation to the rise of animals and the Cambrian explosion. So this ratio alone gives us a huge amount of information about the dynamics through time. So thinking again about the end-Permian extinction, so we have this big injection of magmatic CO2, and this gives us this negative excursion in the carbon record. And we know from quite detailed work on exceptionally well-preserved bits of carbonate where we can extract information that we had a global warming of about 8 to 11 degrees, so very, very rapid global warming. So here you can see this, and in this case, the temperature, there are two major pulses of this extinction event, one with a minor warming and one with a major warming event. Now, remarkably, when you get incredibly well-preserved shell material like this, there are also tiny structural infidelities, or not infidelity, imperfections. And these imperfections contain seawater and gas inclusions. You can measure that directly by crushing the shell in a pulsed way. It gives off this ancient Permian or whatever gas. And this study, using this technique, showed that this first pulse was a slight increase in methane, but the second pulse was an increase in CO2 and then the expected runaway greenhouse thereafter with the release of the methane from the gas hydrates. So we think that this global warming was genuinely due to this runaway greenhouse, CO2 and methane. Now, the other thing that happens when you have very, very rapid global warming is that you have stagnation of the oceans. They start to stratify, they don't circulate so rapidly, and you have widespread depletion of oxygen in the shallow marine oceans, and this leads to anoxia. So anoxia is just simply a lack of oxygen. It's also the name of a death metal band I discovered in Norway. And if you look at the rocks, so here's the Permian rocks. These are actually reef limestones, and there's a dramatic change in the geology. It's very, very obvious all over the world that something very catastrophic has happened. And these sediments formed after this extinction here are full of organic matter, and they show that they were deposited in anoxic waters. And this is almost certainly the major mechanism for the extinction of the biota. So it's almost certain that we certainly have global warming, we certainly have ocean anoxia. But what about ocean acidification? That's the third horseman of the apocalypse. So what is, how do I move this? Oh, there we go. What's ocean acidification? So really all it is that gaseous CO2 in the atmosphere is in equilibrium and becomes aqueous CO2 in the sea. This combines with water to form bicarbonate ions, but so doing liberates, producing bicarbonate ion, but these are unstable and they dissociate to liberate a proton, which of course is a source of acidity. This is unstable again, and it dissociates to carbonate ions, and they produce a source of acidity. So as you pump more CO2 into the sea, once it gets beyond a certain tipping point, you cascade down this train and you produce a lot of acidity in the form of these protons. And in fact, so in other words, the pH of our oceans is maintained by these three sources of carbon. So CO2, bicarbonate, and carbonate ions. And they're the buffering capacity, and that's how they maintain this pH. So pre-industrial pH is about 8.2. And we've already shifted down now to 8.1. It doesn't sound like very much, but it's a logarithmic scale, so it's actually quite a huge amount. In other words, what's happening is you pump more CO2 into the system, the ability of the sea to contain this carbonate ion starts to decrease, and the whole system is shifting. And that is pH. So the ocean acidification is really about the rate of CO2 pumping into the oceans. It's not about absolute amounts of CO2, but just the rate of CO2 increase. It's bad news because it basically leads to all sorts of metabolic problems, and particularly stops animals from forming shells and corals from calcifying. And the problem is, though, that it leads to these synergistic pressures. It can be combined with high temperatures, and once you knock out a key bit of an ecosystem, it can cascade and just degrade. And that's what's of particular concern with coral reefs today. So there's a huge amount of work going on to try and understand how things that produce calcium carbonate, remember this is an enormous store of carbon on the planet, how they respond experimentally. So these are corals being grown under different CO2 conditions. This is a natural CO2 seep. There's a lot of work going on there with understanding the response. And also modelling of the combined effects of CO2 increase, these are parts per million, and global warming. We're already at 415, I think, this year. So it's going up really quite rapidly. But the problem is trying to get at ocean acidification in deep time, the geological record of ocean acidification. We obviously can't measure it directly. So we have to use a proxy. And one of the main proxies we use are boron isotopes, because conveniently these two isotopes, boron 11 and boron 10, they have a different frequency of a fractionation, or the ratio is entirely driven by pH. So if you can measure this ratio, you can back out the pH of the oceans. So here's modern day seawater, here's the ratio here, and there's a relationship between seawater and the carbonate that you measure, and you can work out changes in pH in deep time. So this is what this PhD student Matt Clarkson did for his PhD. We went to Oman and the United Arab Emirates, and this particular site here, Wadi B, it was an unknown site and had a tremendous record across this key, well, actually the two extinction intervals. And this is where it would have been on the edge of the main ocean of the Permian. And we did a lot of careful sampling. This is the carbon isotope record. Here's the first extinction and the second. They're about 60,000 years apart. And what was surprising is that there was no acidification with the first event, but look at the boron isotopes, they become really depleted very, very rapidly, and then actually recover quite rapidly over about what we believe was about 10,000 years. So we had a very short, sharp acidification event that was associated with this second extinction, which really knocked out a whole set of other biota that had survived the first extinction. So without doubt, we had a runaway greenhouse at this time, caused by this Siberian traps. We had global warming, ocean anoxia, and certainly ocean acidification, but in the second extinction, not the first. Now, what I found particularly interesting, it was the first time I'd worked with Earth systems modelers, and this is the group in Exeter, Tim Lenton's group. And what they were able to do is take the record that we had, here's the record of the boron isotope showing this acidification, and create it using everything we knew about the configuration of the Earth, rates of organic matter burial because of this anoxia and global temperature rise, and create two models of the amount of CO2 that was driving the whole process, the extinction event. And we tested two models, a low CO2 model and a high CO2 model. It's very difficult to constrain the absolute amounts of CO2 in deep time, but this is sort of our minimum and maximum. The minimum is about 3 times present atmospheric levels, and the maximum was about 10. And in fact, it was the low CO2 model, the red line, that fit the data best, these data best. So you can see here the red line was mimicking this acidification event very, very well. So we could extract two things from this. One is actually the relative amount of pH change, and we went from probably a background of about 8.2 down to about 7.6, which is a really very, very horrendous pH change. But more importantly, what this modelling allows you to do is actually work out the amount of CO2 that's actually produced above the background amount over this interval. And in effect, we worked out that over this interval was about 24,000 petagrams of carbon was produced from the Siberian traps. Now, interestingly, that's almost exactly the same as if you burn all fossil fuels and all unconventional fuels today. It's almost exactly the same figure. But the critical thing, it was done over really a much longer period of time, 10,000 years. So this is the amount, in other words, the magnitude is the same, but the rate is really quite different. So here's our model of the pH change over those 10,000 years, going from probably just above 8.2 down to about 7.6. But this is the current trajectory today, much, much more rapid, going from 8.2 to 8.1 today, so pre-industrial 8.2. So we've had a change of 0.1 in about 150 years or so. So is this a future analogue, or am I just being miserable? Is this doom-mongering? Well, probably a little bit of both. This is just the latest IPCC projections for temperature. You're probably all familiar with them. But the interesting thing is now the understanding of the physics of the system is getting better and better, of the Earth climate. But of course, the feedbacks and the fluxes are still really quite poorly constrained. Another thing is that the system I've just explained to you, this mass extinction, a very long time ago, it was a world in which many of the biota that we have today simply hadn't evolved. And one of the key things is these tiny, inconspicuous-looking algae. They produce a calcareous skeleton, but these are responsible, one of the major features that actually buffers the ocean today, because they produce a huge amount of calcium carbonate in the open ocean, and that actually also helps to maintain a source of alkalinity, because as they die, they dissolve and they produce CO2. And what's rather interesting is a recent study, and we had suspected it for a long time, is if you look at the rate of extinction through geological time, you can see that actually things are getting better about being more resilient to mass extinction. In other words, the rate of extinction has decreased through geological time. And that's probably because the biota are constantly getting removed by mass extinction, and the new forms that appear are more in equilibrium with the new Earth state as it evolves. So rather than leaving you with a miserable message, the Earth on a geological scale is becoming more resilient to mass extinctions. Of course, this doesn't mean anything for our current crisis, but in the eye of eternity, things are getting better. Okay, thank you.